My name is Megan. I have been a forensic drug chemist for almost 10 years. I have worked in 2 labs at different levels of government. I have a bachelor and a master's of science in chemistry. My duties as a drug chemist include testing pills, powders, paraphernalia, and plant material for the presence or absence of a controlled substance. I issue reports and testify in court. The next topic I'm going to discuss is the techniques we use to analyze evidence. So this video will be a little bit higher level science. If there's anything that you don't understand or I don't explain clearly enough, don't hesitate to leave a comment and I will try my best to explain it a little bit more thoroughly. So every lab that I know follows the recommendations of the Scientific Working Group for the Analysis of Seized Drugs, also known as SWGDRUG. SWGDRUG is an international working group of forensic scientists that was formed in 1997. Their mission is to recommend minimum standards for forensic examination of seized drugs and seek international acceptance of these recommendations. SWGDRUG has broken down analytical techniques into 3 categories based on what type of information the technique gives regarding a sample. Category A gives structural information. Category B gives information about the chemical or physical characteristics. Category C gives general or class information. Category A is at the top of the pyramid because it can give the most specific or selective information about the sample being analyzed. I will only be discussing Category A with this video. So Category A, first one is infrared spectroscopy. This is an analytical technique that provides information about a substance using interactions between infrared light and matter. Atoms bond to other atoms to form chemical compounds. These atoms and bonds are constantly moving at frequencies that are specific to that bond and compound. These frequencies are in the infrared area of the electromagnetic spectrum, specifically the mid-infrared section of the infrared spectrum. IR light is shown through a sample. The compound will absorb some of the frequencies of light, which will excite the vibrations. The detector can tell which frequencies are absorbed because they will be missing from the light the detector receives. The information gathered from the detector is then plotted, giving the IR spectrum unique to that compound, a fingerprint, if you will. The plot shows what frequencies of light were absorbed, which translate into which vibrations were excited when the light passed through the sample. In my experience, this technique works best and easiest with pure compounds. Otherwise, the fingerprints would basically overlap, and it would be difficult, though not impossible, to tell exactly which frequencies were absorbed by which compound in the mixture. Most labs have what's called a Fourier transformed IR, otherwise known as FTIR. FTIR employs an interferometer to check all the wavelengths at once instead of the original time-consuming way of just checking one wavelength at a time. But the data produced must be Fourier transformed, which is a mathematical operation to make it look like a traditional spectra obtained in IR. There are 3 ways absorption can be measured in IR. Transmission, which is a technique where light is passed through a sample. This technique can be a little difficult since if the sample is too thick, the light cannot pass through the sample, giving poor quality or messy spectra. This is also known as total absorbance. Sometimes samples will be diluted to help eliminate issues of total absorbance, but whatever the sample is mixed with needs to not absorb the same range of frequencies as the sample, as what you're interested in the sample. Dilution will usually mean the sample is destroyed. The next measurement technique is called attenuated total reflectance, or ATR. ATR is possibly the most widely used technique and has all but replaced transmission. The FTIR instruments that I have used have all employed this type of measurement. The sample is essentially squished by a crystal and the light passes from the source into the crystal to the sample, then back through the crystal on its way to the detector. With this method, light doesn't actually pass through the sample. The frequencies not absorbed will more or less bounce off the sample, and this method also requires minimal sample preparation, and the sample can be recovered after you're done with the analysis. The third technique is reflectance. This technique also has 3 ways to employ it in its sample analysis. The IR light can be passed through a thin sample, then onto a reflective surface, and then reflected back towards the detector, called reflection absorption. Or the reflective surface is the sample being analyzed, and this would be called specular reflection. Or lastly, light is scattered off the surface of a sample called diffuse reflection. The next technique would be mass spectrometry. This is one half of the main workhorses of most labs. How I explain this technique in court is an unknown sample is injected in the MS, it is blown apart into fragments. These fragments produce a unique fingerprint spectra for that molecule. The more in-depth description would be under a very strong vacuum. A vacuum is necessary to prevent air particles from interfering. A sample is vaporized, which would be sample injection. Then it goes to the ionization chamber, which is the blown apart part. Atoms and molecules in the sample are then hit with a stream of electrons, and some of these hits will knock off one or more electrons, making a positive ion. These ions are then forced out onto the rest of the instrument by the slightly positively charged ion repeller. These ions are then accelerated through 3 slits with varying voltages to accelerate them into a focused beam. This beam is then passed through an electromagnet. The electromagnet will deflect ions depending on how heavy the ions are and what the charge is on the ion. Thus, they are sorted by their mass to charge ratio. Ions that make it through the magnet get to the detector. The detector is basically a metal box that once the ions hit the walls, they are neutralized by an electron jumping from the metal to what was the ion. The flow of electrons causes a current which is amplified and recorded. The ions that were deflected by the magnet can be detected by varying the magnetic field. This varying field is used to calculate the mass to charge ratio. Since the mass of the ions is related to the size of the electromagnetic field used to get it to the detector, and the record of the current will give the number of ions, all this information is used to produce a diagram which plots the abundance of each ion versus its mass to charge ratio. The next technique is nuclear magnetic resonance spectroscopy, which is also known as NMR. This technique measures the resonance of certain atomic nuclei when subjected to a strong stationary magnetic field. Resonance is the selective absorption of very high frequency radio waves. Different atoms within a molecule resonate at different frequencies. Nuclei consist of neutrons and protons, which have a property known as spin. If an atomic nuclei has an even number of protons and neutrons, they have a zero spin. And if they have an odd number, they have a non-zero spin. This could be negative or positive. Molecules with non-zero nuclei have a magnetic moment, which means the nuclei act as a tiny randomly oriented bar magnet. In NMR, a sample is placed in a magnetic field which forces an alignment with or against the external field. Within that magnetic field, radio waves are used to promote transitions in energy levels, which, if we think about the bar magnet, it will spin the other direction. So north and south will be oriented opposite of how they previously were before the change in energy. A computer will compile the radio frequency information, the external magnetic field, the nuclei spin, and the magnetic moment produced, and a spectra that is unique to that compound will be produced by the Raman Spectroscopy is a technique that involves shining a laser at a substance and analyzing the light scattering off of it. Analysis of the light scattering can provide information about the structure of a compound. Raman is the name of the type of light scattering that is known as inelastic scattering. Inelastic scattering means that the light has a different frequency, wavelength, and color than the original beam of light. Elastic scattering, also known as Rayleigh scattering, means that the light that enters the sample is the same as the light that leaves the sample. The frequencies of light absorbed are unique to the molecule and the type of bond present. A sample is illuminated by a monochromatic laser, which means one color. Typically, it'll be green at 532 nanometers. Some of the light will be absorbed by the sample, which will excite molecular vibrations, causing Raman scattering. The scattering light will be collected by the detector so the new frequency can be determined. The frequency shift, or Raman shift, can be calculated, and then Raman shifts are then plotted, which gives another fingerprint for that substance. The last technique in Category A is X-ray diffractometry. This technique can determine a sample's atomic composition or crystalline structure. X-ray beams are sent through a sample, and the diffraction angle, or the beam's change in direction or angle when it passes through the sample, is determined. Depending on the structure, these beams may constructively interfere, which means they line up with each other when interacting with different planes of the sample, making the signal stronger. Then they can also destructively interfere with each other, which means they cancel each other out. Diffraction angle is then plugged into Bragg's law and plotted. These plots are compared to known libraries to determine the identity of the unknown in sample. This technique has an asterisk with SWGDRUG because it provides the crystalline structure and not the molecular structural information. Bruker also produced an excellent video explaining this technique, and you can find it in the notes. There's a link. And as always, if you have any techniques that you have questions about, or if you have any other topics that you would like me to cover, please leave those in the comments. And again, if there's something that you need explained a little bit more, or with like some more examples of, don't hesitate to leave that down in the comments, and I will try my best to help you out.